Hi everyone, I am Juan Niebles and I'm here to talk about efficient and compositional human event understanding. I am interested in building machines that can visually perceive and understand the world. Many times when we think about visual intelligence, the key abilities that come to mind are abilities to perceive objects and their properties. For example, in this image, we perceive objects such as cake, candles, table, people, the lighter, and so on. But in addition to objects, our experience as humans is deeply shaped by our perception of what happens to those objects. It is really the actions, the events that take place, what constitutes our experience and what becomes memories. Let's take this scene as an example. Let me play the video. In this scene, mom is trying to light up the candles on the cake, and the kids are all around waiting for her to finish lighting up the candles. However, some of the candles seem to be melting, and at the same time, the tool the mom's using doesn't seem to be working. So eventually, she realizes that she may need to find another lighter, and she goes to the drawer. Once she finds it, she'll be able to light up the rest of the candles. But the candles continue melting, and it's almost starting a small fire. The kids are so anxious, all desperate for her to finish lighting up the candles as the cake is almost on fire. The birthday girl is trying to blow the candles, but mom says, "Stop, we really have to sing the birthday song first," which they do very quickly, as fast as they can. And eventually, the girl will blow the candles and the cake will survive. And mom is laughing with relief. So you see, it's not only about our perception of the objects themselves, but this moment becomes memorable for us because of the events that happen and the actions we perceive. So really, event understanding is key for creating memories. But it's not only important in memorable moments. Event understanding is also important in our everyday life. For example, as we navigate the world, we may not only need to perceive the scene, the objects and their properties, but we also need to understand what happens to those objects. What are the other agents in the world doing? And that means event perception changes our expectation of the future. It shapes our planning and shapes our behavior. Also, actions and events disambiguate information. It looks like a tiger is attacking a person. But once we look at the dynamics, the actions, the motions of the event, we're able to understand a completely different story here. It is the perception of this event that helps us understand high-level semantics, such as goals and intentions of the agents in the scene. So events are important and crucial for our visual intelligence, and I am interested in the mechanisms, the representations, the algorithms that can enable computer vision to perceive and understand events. Of course, for computer vision, the question is, how do we go about event understanding? And our starting point are videos, and that's because videos are the natural vehicle to capture events. When we look at the videos that we take and share, we notice that humans are the main subject in those videos. And that's no surprise. As we have discussed, events are central to human experience. They already provide a huge variety, as people participate in many kinds of events, from playing with tigers to working to dancing. So I am particularly interested in videos that depict human events. And let's take one of these videos as an example. Let's say we're going to watch this cooking show. And as we watch the events unfold, I want you to think about what events we perceive with respect to a temporal scale. When we only observe a few seconds, we perceive what I call atomic actions, such as cutting onions or place pasta. As we see more of the video, we perceive that these atomic actions are part of more complex actions. We then realize that there are sequences of these complex actions, for example, as the chef reaches sub goals, such as prepare the sauce. Until finally we see the completion of the making spaghetti task. The key observation here is that events are naturally organized in a hierarchy with part of relationships. with tasks composed of subtasks, and complex actions composed of atomic actions. But this composition doesn't end here, of course. We can see that this idea extends to very, very long events, including lifetime events and beyond. For today's talk, I want to focus on this section of the temporal scale, from simple atomic actions to tasks. And is this partonomy important? If we look at the literature from psychology, we see that understanding the hierarchical structure of events is very critical for multiple human abilities. For example, for building the representation of what's currently happening in the world, for planning one's actions, but also remembering what has happened. So this partonomy seems a critical enabler for event perception in humans. And what could make the case that computer vision systems would require a similar ability and capability to parse and understand event hierarchies. So how does this perspective fit within the world of computer vision? Well, if you look at the community efforts and success, they are mostly focused on the lower end of this scale, while much less is done on the complex and longer temporal end of the spectrum. In fact, here are some of the mainstream successes of computer vision. And most of these stories are about the static world, with a strong focus on objects, scenes, and their properties. When thinking about where that lies within my temporal scale, it is really at the origin, the static world that these methods are dealing with. But we're not even that close to that level of success when it comes to video, as we go up in the scale. So today, I want to share with you some of our own efforts in pushing the state of the art in computer vision, particularly when it comes to the upper ranges in this scale. So let's start at this point of the scale. Let's remember that we want to recognize short actions. And one reason to start here is one way to deal with the compositionality issue is to start by predefining a set of actions of interest, such as cut onions or place pasta, so that they can serve as atomic units for the more complex compositional actions. The key here, of course, is that we need very efficient methods to be able to deal with the long durations that will come after. Okay, so how do we go about efficiency here? So if we look at today's methods for video action recognition, we see that the standard video recognition pipeline starts with a input video clip, which is run through some kind of classification network that produces an output class label. And most networks here are based on expensive convolutional or attention layers. So a path to pursue efficiency is that of looking for alternatives to the convolution operation. And one of those alternatives is using memory shifts as the efficient operation. The core idea is to perform channel-wise memory shift operations and use point-wise convolutions to combine information across channels. The shift operation itself is effectively 0 flops and 0 parameters. And that's because the shifts can be merged into the point-wise convolution layer. In the world of video recognition, TSM has showed a significant improvement in accuracy and efficiency, and really showed that one-dimensional temporal shift can effectively replace the one-dimensional convolutions for temporal modeling. However, the TSM architecture still has some issues. For example, it uses traditional expensive 2D convolutional features, it has heuristic and hand-designed fixed shift operations, and also it uses a fixed allocation across a network, so regardless of depth or necessity. So our goal here is to address these limitations with a new efficient primitive and architecture. To this end, we propose Rubik's Shift, a new efficient primitive for video recognition that learns to perform spatio-temporal 3D shift operations. We design a new efficient architecture that we call Rubik's Net, which can learn an allocation of shift operations under a budget constraint. At each Rubik's Shift layer, we take as input a 4-dimensional tensor with channels, time, height, and width. And for each channel, we perform a 3-dimensional shift operation with no spatial or spatio-temporal convolutions. We consider 3 variations of our proposed Rubik's Shift. Our first Rubik's shift is based on an interpolated shift method, which allows the network to learn continuous valued shift operations. Here, fractional shift is evaluated by interpolation. The second, Rubik shift Q method, represents a direct quantization on top of the interpolated shift method. While this really helps with efficiency by using the quantized shift, this technique does not have a true gradient with respect to the shift operation, and this makes it very difficult to learn well. Our third, Rubik's shift AQ, leverages an attention mechanism to maintain better learning properties during training, but still enables quantization during final inference. The way we do this is that during training time, we parameterize the shift operation with an attention distribution. And since shift operations can still incur latency, we formulate a novel global budget constraint loss. We gradually anneal the softmax temperature during training and convert the final one hot attention to discrete shift for final inference. Our main baseline is the TSM architecture. In contrast, RubiksNet has a full spatial-temporal three-dimensional shift, learnable shift operations, and flexible allocation under budget constraint. We compare RubiksNet on several benchmarks, both small and large scale, but we focus here our analysis on datasets that require explicit temporal reasoning for recognition. We report our results on a range of model sizes and accuracy metrics. We observe that our architecture offers competitive performance to the prior state of the art with substantially higher efficiency on both parameters and flops. We also see that for our smallest lightweight networks, we see a large accuracy and efficiency gains, which are important for resource-constrained action recognition. We also visualize the learned spatial-temporal shift operations at different layers. We see that RubiksNet learns to have a conservative shift early in the layers, while progressively capturing larger and larger receptive fields deeper in the network. Finally, I really want to encourage everyone to use RubiksNet. We have released our code and models with a very easy setup using pip install. We have released accelerated CUDA kernels, which are easy to use on PyTorch pipelines. RubiksNet offers really advantages on compute and accuracy and improvements on this front over existing methods on the PyTorch model zoo. There is really no reason not to use RubiksNet, so please visit our website below. So that's what we have been doing in terms of efficient methods for video recognition. However, there are still some limitations. We're still dealing with black box networks, and actions are thought of as monolithic entities, while time is just one more dimension. My hypothesis is that to really make progress on this temporal scale, we have to think about temporal reasoning in a more fundamental and compositional way. We need to study ways to leverage and exploit the compositional nature and properties of videos. So with that in mind, let's talk a bit about what we're doing about recognition of atomic actions. Let's look at this clip of a person sitting down on a sofa. We want to think about what are the cues for recognizing this action. One way to think about it is that in each frame, we see a person and a sofa. And we also perceive their relationships and how they change through time, until we see that the person has performed the action sitting down on a sofa. So how can we build a computer vision system to leverage such decomposition for recognizing actions? Really what we need here is to come up with a new representation, a new database and an algorithm that can help us study this problem. So for that, we introduce Action Genome, which is a representation that decomposes actions into spatial-temporal scene graphs. It also is the first large-scale database that provides action labels and spatial-temporal scene graphs on videos. We built it on top of the Charades dataset, which already provides thousands of videos and hundreds of action classes. But we augmented it with almost 500,000 of object bounding boxes, as well as almost 2 million relationship instances, which come from three types of relationship categories, such as attention relationships, spatial, and contact relationships. So as an example of what we have done, let's take this video. It depicts a person performing several actions, such as drinking from a cup, sitting in a chair, and so on. Each of those actions is already associated with a temporal interval in the video clip. So for each action, we have uniformly sampled a few frames. And on each sample frame, we manually annotate all the objects that the person is interacting with. In each of these frames, we manually annotate the pairwise human-object relationships, which in turn constitute the spatial-temporal scene graphs. This data now captures a lot of the details of how the person interacts with objects and how those relationships change through time. So our goal now is to see, can we build a better action recognition model that leverages this kind of representation? And does it lead to better learning? So to do that, we propose a very simple architecture and algorithm that leverages such decompositions. So we will have a two-branch design. The first branch will process each frame with a scene graph predictor method, which produces a scene graph for each frame in the video. We then design a simple feature that captures the information of the objects and the relationships and how they evolve through time. We call this a scene graph feature bank. The second branch in our architecture will extract global video features using a standard feature extractor backbone for videos. We then merge these two using a feature bank operator to finally recognize actions. So can we build a better action recognition system by using this representation? So we have two key experiments here. First one, we'll evaluate if using our spatial-temporal scene graphs as an intermediate representation can lead to better action recognition. So what we see is that the first table here shows we can improve over the state-of-the-art results by leveraging the representation and the composition. So that's really encouraging. On the other hand, I'm really excited about the potential that our representation has for future learning. Here, we also show that leveraging such compositional representation can improve future learning on new actions with limited training samples. Here we show an example. This video has these ground truth action labels. Prior work, which only uses the global video features, gets confused by the scene information and predicts watching television. In contrast, our method grounds the decision on the objects and relationships, and it's able to correctly predict the action. So that's what we have been doing for atomic actions. However, there are still some limitations. For example, we need supervision for decomposing actions, and we have assumed that we can discretize the actions of interest to a fixed set of tokens. However, this is not always the case, and this is particularly important as we advance in our timescale, where more complex actions are much harder to tokenize into categories. So we may want to rely on, for example, language descriptions. Also, rather than relying on annotations for our graphs, we may want to explore building graphs in a data-driven way and bottom-up fashion from object detectors. So the idea here is that we want to translate bottom-up object interaction graphs into language descriptions. Let's take a look. In this setting, we're interested in the idea of describing videos with sentences. So given this video, we want to produce a sentence such as a cat jumps into a box. There are lots of prior work on video captioning. For example, frame-level approaches, but they tend to ignore object-level information. Others focus on spatial object interaction modeling, but they tend to ignore the temporal transformation information. And those that focus on temporal transformation, they tend to ignore the spatial relationship between objects in a frame. We want to tackle these limitations simultaneously. We want to use object information with object detectors, and we want to model the temporal transformations by linking object detectors across the video. We also want to model a spatial interaction by capturing the relationship between objects within a frame. Using these ideas, we can create data-driven spatial temporal graphs. So the challenge is, how can we robustly create and leverage these spatial temporal graphs from noisy object detectors? One way to do that is using a two-branch design. So we start with our input video, and on the first branch, we will construct spatial temporal graphs that capture object interactions. On the second branch, we'll have context scene branch, which captures holistic video cues. Finally, these two will be fused into a language model to generate captions. So that's an interesting and simple idea. However, there is a complication, and that is the data-driven graph can be quite noisy. For example, the graph size can vary a lot from video to video, and that tends to lead to representations that are very noisy. So how can we take advantage of this without the unstable issues? So a solution to that is we want to use late fusion by knowledge distillation. So the high-level idea is that we don't want to use both branches during inference time. Instead, we want to leverage the object branch only for training. So to achieve that, we will distill the knowledge from the object branch into the scene branch. The idea is that the object branch will induce object knowledge into the scene branch. And in our experiments, we find that the learned features in this way become much more robust. An advantage is that at test time, we only need to use the distilled scene branch. But because it's been induced with object knowledge, we find that it produces better grounding and captions. We test this on a couple of benchmarks. Let me briefly mention the quantitative results by saying that we achieved a state of the art on two competitive datasets. But a really interesting result is on the groundings that our model does to produce the captions. Given an input video, the baseline method that only uses the scene branch doesn't produce very meaningful groundings. In contrast, our model better attends to the relevant objects in the video, and as a result, our captions are more accurate. We observe that this result is consistent across many examples in the benchmark. Okay, so we show that we can use data-driven spatial temporal graphs for capturing videos. And our distillation process produces better feature learning and is quite effective in the benchmarks. So that's an example of how we can use data-driven graphs and use language to describe actions that are more complex so that they cannot easily be tokenized into categories. However, there are still some limitations. For example, the language descriptions need to be just right in terms of length and expression of composition. Furthermore, sometimes we may be interested in extracting the structure of the event in the video, not just describing them. And this is particularly important as we move up in our temporal scale to tasks and subtasks, where understanding and extracting the event structure from the video is an important goal. We studied this problem of extracting event structure in the setting of instructional videos. The idea is that starting with a step-by-step decomposition of the video into segments with corresponding descriptions, we want to produce a more grounded causal dependency structure graph with two key components here. One, we try to discover the dependencies between steps, and second, we want to have grounding of the objects from the instructions in the video. So let's say that you're watching an instructional video, for example, for how to make a Caesar salad. And some of the steps that may be involved in this task are, for example, mixing the salad greens and also taking them. However, how do we achieve this idea of grounding and dependency resolution? Well, the key to solve that is that we have to embrace multimodal reasoning of the spoken instructions in the video data so that we can interpret what the structure is saying and how that relates to the image. For example, in this case, there are two things we want to do. We want to ground the pronouns and nouns into the image, right? So in a formulation, that's equivalent to inferring the correct blue arrows that relate words into the specific objects in the frame. And that's of course not trivial because sometimes the instructor may use pronouns such as it. And the second thing we want to do is to resolve references, where we want to find the relation between the spoken sentences from one to another. And the way to do that is we want to do this joint grounding and reference solution so that we're able to extract an approximate relational graph of the events in the video. Without much details, a key to our method is that we want to achieve this without supervision on the grounding arrows or the reference arrows. But that means we need to solve these two tasks simultaneously during training. For that, we use an alternative EM-like approach to solve one task while holding the other task fixed. To give you an idea of our results, we have taken this input instructional video for how to make spaghetti and meatballs. And this is our visually grounded action graph output. Our graph relates steps from one another within the procedure, but is also able to localize the objects that are being manipulated within the frame. This is really exciting because the graph is potentially a path towards a more grounded dependency graph structure that really captures the causal relationship between steps in a procedure. Okay, so that's what we have been doing for instructional videos and task understanding. As we are able to parse these tasks better, I imagine two interesting applications. One is virtual coaches for training people, and second, robotic learning for demonstrations. So that's a sneak peek of our progress so far. We have constructed some evidence that exploiting the hierarchical organization of events can be helpful for computer vision. And so far, we have climbed our temporal scale a little bit, but of course, a lot more is needed. And we're still in pursuit of algorithms that can enable machines to understand longer and more complex events, as well as understand those events in more detail. Eventually, we will be able to parse, understand, and summarize a lifetime of events. But there are many open questions. For example, how do we combine visual perception of events with language understanding? Or how do we more precisely define the levels in this hierarchy? And how do we discover the correct units for compositionality? I think these are all interesting questions that we may want to address in the future. And that's all I wanted to share today. I just want to close by thanking and acknowledging the students, collaborators, and sponsors that really made all this work possible. Thank you.